Okay, so today we're going to talk about linear approximation and differentials. And just a word, basically what we're talking about here as far as linear approximations go, is we're going to use a linear function to approximate certain values. Okay, and so I'll talk about what kind of like the relevance of this is, or of the importance, or how things are simplified when we deal with complicated functions and we try to make it into a linear approximation. So let's start off with kind of like an introduction as to what's going on here. So here's what we could, what comment we can make. We could say we know that a curve lies very close to its tangent line near the point of tangency. So basically what we're saying is, if you were to grab any curve, okay, so, and this should just be a tangent C, not tangent C's, okay, so get rid of the I. So if you were to look at this curve, if I have a curve that looks like this, and if I grab a point here, which if we label that point its coordinates a comma f of a, and of course this would then be the function defined as f of x. If I find the equation of the tangent line, which that we were really good at by this point, we could find the equation of the tangent line to this curve through that point, which if I were to draw this out, what do you notice? This tangent line, which we can call it L of x, what you notice is the y values of this tangent line near the point of tangency are very similar to the y values of this function f. So for example, if I were to grab this y value of that function, and if I were to grab the y value of this line, okay, so these two y values, you notice that they're not exactly the same. Obviously, there's a little bit of an error, but they're very close to each other. So what we're basically claiming is that this linear function does a decent job of describing the y values of this function as long as I'm close to the point of tangency. Now, of course, if we go really far away from this curve, like if I take this point, the y value at this x value for this function, and the y value of the line at that x function, you notice that there's a larger gap. So the further away I am from the point of tangency, the worse off the y values of the line become with the function. So what we're noticing is, as long as I'm close to the point of tangency, the y values of the line are very, very similar to the y values of the function f. So in other words, we're using the line to approximate the y values of this function, okay? So what you might notice is, well, what's the point of this? Can't I just find the y values of the function? The answer is, if you can, yes. But the next comment I want to make here is that, see, it might be easy to calculate a value f of a function, but difficult to find values nearby f. Okay, so basically what I'm saying here is, look, finding this point f of a might be easy, right? It might be a simple function, or simple enough where we could plug in a, and calculating the y value at a is simple. But what if I want to find the y value on this function near a, like let's say that point, and we notice that, okay, that's not as simple. So this is where this whole point of the tangent line comes into play, because finding this y value isn't easy, but finding the y value of the linear function is easy. I mean, I think that's something we've been doing since forever, right? So I could give you any x value on a linear function, you could find its corresponding y value. So that's why linear functions are easy to work with. So this idea is actually a really, really interesting idea. It's a cool idea, the way that we're grabbing a line and we're saying, look, this line is very similar to f of x as long as I'm very close to the point of tangency. So kind of like the circle I made right here in this region, this line kind of acts like this function f. So we could use the y values of the line to approximate f. So basically what we're going to say here is that linear functions, or sorry, let's say thus we will use the linear function to do so. So as I was saying, we're going to use the linear function to find the y values of f nearby. So remember what we're claiming here. I'm claiming that this line is an approximation of this function as long as I'm close to the point of tangency. So remember, when we say this line could be used to approximate the y values of this function, we're always under the assumption that we're very, very close to the point of tangency. In fact, the closer I am to the point of tangency, the better off my approximation is. The further I am away from my point of tangency, my error becomes larger and larger and larger. So just keep that in mind. Okay, so basically, let's define what this linear function is, which we've already kind of talked about. So we could say that this linear function that we're talking about is the tangent line of f at a comma f of a. Okay, so what we're saying is we will use the tangent line at a comma f of a as an approximation. So let me underline this. So this linear function is an approximation to the curve y equals, or to the curve f of x when x is near a. So once again, just to point this out, see this linear or this tangent line is a good approximation of f of x when my x values are close to a, where a is the x value of my point of tangency. So remember, the main point we're making here is that as long as you're close to the point of tangency, you're good. You have nothing to worry about as far as the approximations go. Okay, so now here's some review. We know that the equation of the tangent is y equals to f of a plus f prime of a of x minus a. So if you think about this, this is the equation of my tangent line in point slope form. If you remember, it should be y minus f of a, so I just added f of a to each side. But what am I saying? What's f prime of a? That's the slope of my tangent line. A is the x value of the point of tangency, and f of a is the y value of the point of tangency. So this is, in fact, the equation of my tangent line. So using the same equation, what we could say is, and the linear approximation of f at a is the following. And this is the same equation. We're just kind of changing variables. So L of x, which this was the y in the earlier equation, equals to f of a plus f prime of a times x minus a. Okay, so this is actually known as the linearization of f at a. Okay, so one comment I want to make is the following. Here's what we're claiming. F of x, which is the function that we're using this line to approximate. Like, think about the curve I drew earlier. So f of x is approximately the same thing as what? The equation of the tangent line. So what we're claiming is f of x is about the same thing as f of a plus f prime of a times x minus a, as long as what is true. So think about it. We could say that the y values of the function f are about the same thing as the y values of my linear function, or my tangent line, which is our linearization, as long as x is near a. Okay, so as long as I'm close to the point of tangency, the y values of the line do a good job of approximating the y values of f of x. So let's do an example where we'll put this to use. So if you think about it, just to kind of summarize this, all we're really doing is finding equations of tangent lines. That's all we're doing. And then we're plugging in our x values into the tangent line equation to approximate the y values. So what we could say is find the linearization of the function f of x equals to square root of x plus 3 at a equals to 1, and use it to approximate square root of 4.05 and square root of 3.98. So if you look at this, notice how square root of 4.05 and square root of 3.98, we can't find those exact values easily, right? However, if you were to look at this, what square root is it that these guys are close to that I could easily find? And you should know that's square root of 4, right? We know that the square root of 4 is 2, but we don't know what the square root of 4.05 is exactly, okay? So you could see that square root of 4 is easy to find, but square root of 4.05 or square root of 3.98, those aren't as easy. So the first thing we want to do is we want to find the linearization of this guy. So what is it that we want? Which is the equation of the tangent line. That would be, by definition, we know that tangent lines should be like this, f of 1. And remember, our x value that we're focusing on is what? At a equals 1, okay? So L of x equals to f of 1 plus f prime of 1 times x minus 1. Okay, so finding f of 1, f prime of 1, so these shouldn't be difficult. So let's go after f prime of 1, which is the derivative of this guy. So if f of x is x plus 3 to the power of 1/2, what do we have? F prime of x will be 1/2 times x plus 3 to the negative 1/2. Okay, so now I'm ready to approximate or get my linearization. So what do we have? So this implies f prime of 1 equals to 1/2 times 1 plus 3 to the negative 1/2. This becomes what? 4 to the negative 1/2 becomes 1/2. So this will be 1/4. Okay, and then what else do we need? We need f of 1, and we should basically be able to linearize. So f of 1 is about, or what is it that we have? It's just 1 plus 3, square root of 1 plus 3, which is 2. So my linearization is actually going to be L of x equals to 2 plus 1/4 times x minus 1. Okay, and we could simplify this a little bit to make it look cleaner, which becomes what? X over 4 plus 7 over 4. Okay, so here's what we're claiming. Okay, so what we claim is, we claim that what? L of x, which is, so in other words, square root of x plus 3, which is the function that we're linearizing, is roughly the same thing as x over 4 plus 7 over 4, as long as x is near what value? See, what was the value that we linearized at? It was at a equals 1. So as long as x is near 1. Okay, so keep in mind that this line does a good job of approximating that as long as I'm close to 1. If I'm not close to 1, then this does not work. Okay, so what we could do now is we can say, now we want to approximate. So to approximate square root of 4.05, and square root of 3.98. Let's do this. So first of all, I need to make square root of 4.05 look like square root of something plus 3. So if you think about it, we could say, look, square root of 4.05 is, I need to get it to be able to use this rule. I need to get this to look like something plus 3. So how could I break this up to make it look like something plus 3? Well, if you think about it, isn't square root of 4.05 the same thing as 1.05 plus 3? Right now, if you look at this and you compare it to that, see, my x is now 1.05, and this plus 3 is what we needed right there. So what do you notice here? Actually, this is my value, right? It's the 1.05, which is that near 1? And the answer is yes. So what do I know? The approximation that I'm going to make here is going to be a pretty good approximation because 1.05 is very close to 1. So we know it's not going to be exact, but it's going to be a pretty good approximation. So this is roughly the same thing as what? So if x is my 1.05, I'm basically using this line. So it'll be 1.05 over 4 plus 7 over 4, which then if I add them, I get 8.05 over 4. And there's my approximation. So this is approximately 8.05 over 4. And if you want to convert this to a decimal, it's 2.0125, something like that. Okay? So let's look at the next one, square root of 3.98. We're basically doing the same thing. So that's the same thing as what? 0.98 plus 3. Okay, and now look at this. Once again, now that I got this to look like that, once again, 0.98 is near 1. Now my question to you is, what do you think would be a better approximation, or what's going to give me a more accurate approximation, the bottom one or the top one? Okay, why? And think about it. Why would this be the case? Why would one be a better approximation than the other? So if you've already thought about it, between these two, the one on the bottom is going to be a better approximation. How come? Because 0.98 is closer to 1 than 1.05 is. Both of them are going to be good approximations, but the closer you are to the point of tangency, the better off your approximations are going to be. So this is going to be roughly 0.98 over 4 plus 7 over 4, which is about 7.98 over 4, and that as a decimal becomes 1.995. Okay, so if you notice what we're doing here is, all we're really doing is finding the derivative or the equation of the tangent line, and we're using that to approximate. Okay, so let's look at example 2. So for example 2, we're actually going to use a graphing calculator to solve this one. So for example 2, we're going to say, for what values of x is the linear approximation rad x plus 3, which is roughly about the same thing as 7 over 4 plus x over 4, accurate to within 0.5. Okay, so basically here's what we're saying. How far can I go for my point of tangent, the point of tangency, in which this line, the y values of this line and the y values of the actual function are the difference between them is no bigger than 0.5. So in other words, what we're saying is, we want the distance to be less than 0.5. So what does that mean? If you think about it, we're talking about absolute value. So we could say this is what? Square root of x plus 3 minus 7 over 4 plus x over 4 is less than 0.5. And so if I'm working with an absolute value, I know that I could break this up as what? We can say it's going to be, and this is equivalent to square root of x plus 3 minus 7/4 plus x over 4 is less than 0.5 and is greater than negative 0.5. So I just used the rule of absolute values where this statement and this statement are the same thing, right? So what I want to do now is I want to kind of isolate this linear function or leave the linear function by itself. So if you think about it, what we have is if I subtract rad x plus 3 from all sides, what do I get? I get negative 0.5 minus rad x plus 3 is less than negative 7/4 plus x over 4 is less than negative rad x plus 3 plus 0.5. And now, just to get rid of this minus, I'm going to multiply everything by a negative, and these inequalities are going to flip, so I'm going to rearrange them so it works out just right. So basically, if I multiply everything by a negative 1, here's what's going to happen. I'll have 7 over 4 plus x over 4. Now, instead of this guy being less than this guy, it's actually this guy's going to be greater than. So I'm going to move this to the left side. So it'll be this guy is greater than rad x plus 3 minus 0.5. And it's going to be less than this, the opposite of this guy, which will be less than rad x plus 3 plus 0.5. So basically, what are we saying? Look, this guy's been shifted down. Rad x plus 3 is shifted down 0.5. Rad x plus 3 is shifted up 0.5. So whenever this line is between this curve and this curve, then my approximation will be within 0.5. So how do we do that? What we're going to do is now we're just going to graph all three of these. Okay, so let's do that real quick. If I bring my graphing calculator, what is it that we want to graph? The three functions we're graphing are square root of x plus 3 minus 0.5, and then we want to graph 7 over 4 plus x over 4, and then we want to graph rad x plus 3 plus 0.5. Okay, so let's graph this and see how my window size looks. I might need to adjust my window size. Okay, so there's the line, and so I probably need to zoom out just to see where they intersect each other. So this is the line. These are the two curves. So I want all the x values where this line is between those two curves. So let's zoom out a little bit so we can see what that looks like. Okay, so there's my rad x plus 3 plus 0.5. There's the line, and there's the other one. So, and in fact, you notice that they intersect here and here. So anywhere between this x value and this x value, the line is between the two curves. So let's focus in here and find that x-intercept. So once again, let's zoom in that region, which is somewhere around here. Let's press enter. I want that point of intersection. So there's the square root, and there's the point of intersection. So notice how this line is between those two curves there. So if you remember, how do we find the point of intersection? You go to second calc, you go down to intersect, and then you make sure you're on the right curve. See, this curve doesn't intersect the line, so press up. Now I'm on the top curve, so press enter as long as you're near the point of intersection. And then you should go to the line, because you want to find the point of intersection between the line and the curve. So if I press enter, and then you press enter a third time, and the first x value is what? Negative 2 let's call it 66. So it'll be when x is greater than negative 2.66. Okay, now to find the other point of intersection, we can zoom out again and then find the other point in which we have the intersection. So let's zoom out. Which is somewhere around here, it looks like. So let's zoom in there. I mean, it's kind of difficult to see right now, but once we zoom in that region, it'll probably be easier to see what's going on. So let me move a little higher up. Okay, so I'm interested in zooming into this region. So if we do that, we should probably see a point of intersection somewhere around here. And yeah, there it is. So it looks like it's somewhere here. So if we go to second calc, intersect, just make sure you're on the right curve. So I want to go up, go close to the point of intersection. That's close enough. Press enter. and then go even closer. So press enter for a third time, and there it is, which is about 8.66. So this has to be less than 8.66. So as long as my x values are between negative 2.66 and 8.66, then my approximations are going to be accurate to within 0.5. Okay, so the last example we're going to do, and then we're going to leave off here, which is, this is actually a very interesting example. You'll see why. I want you to find the linearization of f of x equals to sine x at a equals to 0. So take a minute and try to do this on your own. Pause the video, try to do this on your own, and then when you find it, then press play and see if it matches up with what we're doing. Okay, so if I take the linearization of f of x equals sine of x, I need to find basically the equation of the tangent line to this curve at a equals 0. Okay, what is it that we know? By definition, our linearization, which is the equation of the tangent line, that's all it is. It'll be what? F of 0 plus f prime of 0 times x minus 0. So what do we notice here? F of 0, that's not hard to find because f of 0 is just strictly sine of 0. And sine of 0 is 0. And then we need to find f prime of 0. Well, f prime of x, which is the derivative of sine x, that's just cosine of x, which means f prime of 0 is cosine of 0, which is 1. Okay, so now I have everything I need. So the linearization is going to be what? It'll be 0, so I'm not going to write that, plus, which who cares, 1 times x minus 0. So 1 times x minus 0, which is just x. So what is it that we're claiming here? So what we're claiming is that sine of x is about the same thing as what? X when x is near 0. How cool is this? Do you guys see what this is? If you remember earlier on in this class, what did I do? I gave you this. I said, what is this? Limit as x approaches 0 of sine x over x. And what is it that we said? This was 1. How come? Look at what we just showed. We said as long as x is near 0, sine of x is roughly the same thing as x. So what is this claiming, this linearization? These two are roughly the same. And if they're the same, we can say that this is roughly the same as what? Limit as x goes to 0. And we could substitute. We could say, in place of sine x, replace it with x because they're roughly the same thing. So what we get here is what? X over x, which basically just becomes 1. So here's a perfect example as to why we're showing, or why we see that the limit as x approaches 0 of sine x over x is 1, because our linearization is suggesting that. It's saying, look, sine of x is roughly the same thing as x as long as you're close to 0. So these two are about the same thing. So I hope you appreciate this. I mean, I'm just getting excited kind of like looking at this and how it works. But that is basically what it is. I mean, hopefully this limit is starting to make more sense to us, because if you understand the whole process of linearization, if this makes sense to you, then this is exactly what this limit was claiming. Okay, now with that said, we will come back to this limit again in the future, and then you'll see how there'll be other ways we could show how this limit is just 1. Okay, but here's an example as to why this limit works the way it does. Okay, and this was shown through linearization. So what do we notice? As long as you're near 0, sine of x is roughly the same thing as x. Okay, so that's where we're going to stop today. We have a second part of this section which we'll talk about tomorrow. Okay, so that's basically it. Make sure to ask me any questions that you may have about linearization.